Hello everyone, welcome to this presentation on eigenvalues and eigenvectors. In this presentation, we will understand how a matrix transforms vectors, why some vectors become eigenvectors, and how eigenvalues are obtained. First, look at the concept diagram on the screen. Matrix A is a transformation matrix is shown here, and X is the input vector. Transformation matrix A transforms the input vector x into a new vector called the transformed vector ax. Under this transformation, a vector may behave in two ways: as a general case, as a special case called eigenvector. For a general vector, the transformation usually changes both its length and direction. Here, the green color arrow is the input vector, blue color arrow is the transformed vector. So transformed vector Ax is not parallel to the original vector x. Therefore, Ax is not equivalent to the scalar multiple of x, or Ax is not equivalent to the lambda x. This is the general case where the direction line is not preserved. But if the vector satisfies the Ax equals to the lambda x, then that vector is called an eigenvector. For a special vector called an eigenvector, the transformed vector Ax remains on the same direction line. You can see here the green color arrow shown here is the input vector. Extended portion shown here is on the same line. Only scaling occurs, so Ax is in parallel with the input vector x, and Ax is equal to the scalar multiple of the input vector x. Here x is the eigenvector and lambda is the corresponding eigenvalue. Rearranging this eigenvector equation for a non-zero eigenvector x, we can get the characteristic equation as determinant of a minus lambda I equals to 0. This is the characteristic equation used to find the eigenvalues. And this particular equation Ax equals to lambda x is the eigenvector equation used to find the eigenvector. In the next slide, we will discuss the key concepts of eigenvalues and eigenvectors at a glance. Let us first understand the basic ideas and important properties of eigenvalues and eigenvectors. The first set is transformation of a vector using a matrix. Here x is the input vector, A is the transformation matrix. Whenever this matrix A acts on the input vector, it produces a new vector called transformed vector, that is Ax. Usually this transformation changes both length and direction of the vector. In case of general vector, new vector Ax is not parallel to the original vector x. So Ax is not equal to the lambda x. But eigenvectors are special vectors. When a matrix transforms eigenvector, it its direction stays completely unchanged. This vector is simply scaled by a factor of lambda. This gives us the fundamental equation that is known as the Ax equals to lambda times x. Lambda times x means scalar multiple of the input vector x. Here only scaling occurs. The next set is the two important equations of eigenvalues and eigenvectors. The first equation is the characteristic equation which gives the eigenvalues. Determinant of a minus lambda I equals to 0. Here lambda is the eigenvalue. The second equation is the eigenvector equation known as a minus lambda I times vector x equals to 0. Eigenvector equation gives the eigenvectors corresponding to the eigenvalues found in the characteristic equation. Once we find the eigenvalues and their corresponding eigenvectors using these two equations, they can be verified using the two eigenvalues properties. The first property is sum of the eigenvalues will always equal to matrix trace. You can see here sum of the eigenvalues equals to the trace of the matrix A. The second property is eigenvalues product equal to its determinant of A. The last property is eigenvalues of A inverse are the reciprocal of the eigenvalues of matrix A. Next slide, we compare a general vector and eigenvector using graphical and numerical examples. This slide presents the effect of the same transformation matrix M on two different input vectors u and x. The two diagrams shown here help us to understand how their transformed directions differ. The first case is general vector u shown in the upper diagram. Here u is input vector is 1 0, transformation matrix is M 2 1 1 2. After applying the transformation matrix M, the transformed vector mu becomes 2 1. Here the transformed vector which is shown in the red color changes both in its length and direction. Original vector u lies along the positive x-axis. The transformed vector after multiplication with the m is known as mu, changes its direction as well as its length. The vector mu, which is the transformed vector, is not a scalar multiple of u. You can see here. Therefore, we cannot write 2 1 is not equivalent to the lambda times 1 0. Therefore, mu is not equivalent to the lambda u. So, the vector which is general is not a eigenvector. Therefore, u is not a eigenvector of M. Coming to the second case, eigenvector x. Now consider the special vector x 1 1 is shown in blue color and is shown in the lower diagram. We apply the same transformation matrix M, which is 2 1 and 1 2. After transformation, the transformed vector mx becomes 3 3. But now you see here mx, which is 3 3, is equivalent to a scalar times original input vector 1 1. Therefore we can write mx, that is transformed vector, is equal to the scalar multiple of the input vector x. Here the scalar value, which is 3, is nothing but the eigenvalue, that is denoted as lambda, which is equal to the 3. You can also observe here, in case of eigenvector, the direction line remains unchanged. Only scaling occurs. The scaling factor is known as the eigenvalue. Therefore, we can say that mx equals to lambda x. This eigenvector idea leads to the standard method for finding eigenvalues. You can see here the characteristic equation, that is determinant of the m minus lambda I equals to 0, help us to find the eigenvalues. Similarly, after finding the eigenvalue lambda, the corresponding eigenvectors are obtained from m minus lambda I times x, which is equivalent to 0. This is the eigenvector equation. Here x is the eigenvector, m is the transformation matrix, lambda is the eigenvalue. Thus, a general vector changes direction while an eigenvector remains on the same direction line and only gets scaled. You can see here. In the next slide, we will apply these two equations to solve the simple gate style eigenvalue and eigenvector problems. Now let us find the eigenvalues of the given matrix A 2 1 1 2. To find the eigenvalues, we form the characteristic equation first, which is nothing but the determinant of A minus lambda I equals to 0. Subtracting lambda from the principal elements, which gives determinant of 2 minus lambda 1 1 2 minus lambda, which is equivalent to the 0. Cross multiplying the diagonal elements, since it is a 2 by 2 matrix, we get 2 minus lambda times 2 minus lambda minus 1 times 1, which is equivalent to 0. Expanding this gives characteristic equation in quadratic form, lambda square minus 4 lambda plus 3 equals to 0. So factoring this quadratic equation yields lambda minus 3 times lambda minus 1 equals to 0. Therefore, the two eigenvalues we can found, they are lambda 1 equals to 3 and lambda 2 equals to 1 from this equation. Now let us quickly verify them using two important properties which will be helpful in gate examination. There are two important eigenvalues problems. First property is sum of all eigenvalues equal to the trace of the matrix A is the first property, and the second property is product of all eigenvalues equal to the determinant of the A. First we use the first property, sum of all eigenvalues equals to the trace of A. If you find trace of A equals to the, this is the A vector A 2 1 1 2, trace is 2 plus 2, which is equal to 4. And if we can find the sum of all eigenvalues that we have found, which are 3 and 1, sum is 3 plus 1. So this property is satisfied. Coming to the second property, product of these two eigenvalues, lambda 1 and lambda 2, which is equivalent to 3 times 1, equivalent to the determinant of A. If you can find the determinant of A, which is nothing but the 2 times 2 minus 1 1, equivalent to 3. So this property is also satisfied. That is, product of all eigenvalues is equivalent to the determinant of A. So both properties are satisfied. Therefore, the eigenvalues are correct. So we have found the eigenvalues and verified the eigenvalues. Now let us find the corresponding eigenvectors in the next slide. Now let us find the, the eigenvalues found in the previous example for the matrix A equals to 2, 1, 1, 2. The eigenvalues found in the previous example for the matrix A equals to 2, 1, 1, 2 are lambda 1 equals to 3 and lambda 2 equals to 1. From the first eigenvalue lambda 1 equals to 3, let us find the eigenvector. Substitute lambda 1 equals to 3 into the eigenvector equation, that is A minus lambda I times vector x equals to 0. So it will become 2 minus 3 1 1 minus 2 minus 3 times vector x equals to 0. Simplified to minus 1 1 1 minus 1 vector x equals to 0. From the first row we get the simple linear equation as my first row vector x column minus x1 plus x2 equals to 0. This gives x2 equals to x1. Taking x1 equals to 1, we get x2 equals to 1. Therefore, the first eigenvector is x1 equals to 1 1 for the eigenvalue lambda 1 equals to 3. Now let us find the eigenvector for the eigenvalue lambda 2 equals to 1. First, substitute lambda 2 equals to 1 in the eigenvector equation A minus lambda I times vector x equals to 0. This gives 1 1 1 1 times x1 x2, which is the vector eigenvector x equals to 0. So this gives us x1 plus x2 equals to 0. Taking x1 equals to 1, we get x2 equals to minus 1. Therefore, the second eigenvector corresponding to the eigenvalue lambda 2 equals to 1 is 1 minus 1. So we have obtained both eigenvalues and their corresponding eigenvectors. In the next slide, let us see a useful gate shortcut related eigenvalues of the inverse matrix. Let us solve a simple gate style question. The question is, let A be a 2 by 2 real matrix. The eigenvalue of a matrix A are given as lambda 1 equals to 2 and lambda 2 equals to 5. Find the eigenvalues of its inverse matrix. That means eigenvalues of a matrix A are given and we are asked to find the eigenvalues of the inverse matrix. Now the solution is, suppose we have eigenvalues of A are lambda 1, lambda 2 dot dot lambda n. Then eigenvalues of A inverse are reciprocals of the eigenvector A, which is equivalent to 1 by lambda 1, 1 by lambda 2 dot dot 1 by lambda n. Therefore, we can find 1 by lambda 1 as 1 by 2 as lambda 1 equals to 2, which is equal to 0.5, and 1 by lambda 2 as 1 by lambda 2 is 5, that is 1 by 5 equals to 0.2. Hence, the eigenvalues of A inverse are 0.5 and 0.2. So that's all. So we do not need to find A inverse separately in this problem. Thus, for inverse matrices, the eigenvalues becomes reciprocals. In the next slide, Let us quickly revise the important points.